Hello there. Welcome to Grade 11 Chemistry. In this lesson, we're going to review some different aspects of atoms that will be useful to you throughout this course. So hopefully everybody remembers what atoms are made of. We have here some protons, and we have some neutrons, and we have some electrons in layers. And it's the differences between these subatomic particles that make differences between atoms and give them their properties. So that's the heart of everything we do in chemistry, and so we're going to look at some of the very basics of how these subatomic particles differ from particle to particle. So starting off, when you look on your periodic table, you see two numbers and you see values given there, and those values relate to the different types of atoms that you can have. So different elements are going to have, different atomic numbers. Ions are going to have a charge, and isotopes will have different masses. Bohr-Rutherford diagrams can be useful when we are looking at the structure of atoms and considering how one atom differs from another. So sometimes we'll use that model. The other type of representation is Lewis dot symbols. And so usually for bonding, this is the most useful thing. And so if we have an element here with 9 protons, that's fluorine. And then we can arrange the valence electrons around it. Just make sure you put them on sort of 4 corners first, and then double them up until you're finished. Yeah, once you have your valence electrons on, you're good for all sorts of things, usually relating with bonding. So differences in the subatomic particles is what gives us different elements, ions, and isotopes. So I just wanted to remind you of what particles went with which type of particle. So we have 9 protons here, so that makes this fluorine. And if we compare that with this element over here, everything else is the same except the number of protons. So if you change the number of protons by whatever means, or if we're just comparing two atoms, then you have a different element, right? So that'll be neon instead of fluorine. If you change the number of electrons, you see that this particle here has all the same particles except it has an extra electron. That means that this is now a charged atom because there are more electrons than protons, and so negative charge, and that makes it an ion. The last thing that can differ between particles is the neutrons. So still 9 protons, so still fluorine. Only instead of fluorine with a mass number of 19, this is fluorine with a mass number of 20. So that makes it a heavier isotope, still the same element. So you'll recall that ions form when electrons are either added or removed from atoms. They will be added or removed in order to produce a stable outer shell of electrons. And so you can see on the right-hand side here, all these nonmetals that aren't noble gases all end up with a negative charge when they gain electrons to become more like a noble gas. And then everything else over here, when they become ions, they become positively charged. All your metals do that. And you can see that there are some that have more than one possible charge. And that's because the electron arrangements, once you get past this, first 20 or so, there starts to get a little more complex. Well, we'll learn about that in later units. And you can see that the result is there's more than one way in which they can become stable. So the only difference between different isotopes of the same element is the number of neutrons. They'll react the same way, they'll bond the same way. Just the extra neutrons or missing neutrons makes their mass a little different. These two isotopes that are represented down here are both lithium because they both have 3 blue protons, right? So both with a little 3. And then you can see that the total number of particles differs. So this is lithium 6, and over here is lithium 7. So the one on the right will be a little heavier. And you can use that property to separate isotopes if you have the right technology. So a device that's used to separate them based on mass is called a mass spectrometer. And it's a very clever device. Generally, a high school wouldn't have one, but if you go to universities, they'll definitely will. And what happens is you'll put your lithium sample in here and vaporize it, so like heat it up until it turns into a gas. And then you ionize it too, which means you like pass a bunch of electricity through it and knock off a bunch of electrons. So now it has a charge. So then you have these charge plates. So if we knocked off electrons, it'll all be positive. So if you charge these plates negatively and you poke a little hole through them, then you'll get this stream of isotopes coming out of here. And then you have this magnetic field that the stream of isotopes has to pass through, and it will deflect this beam of particles as it passes through. Now, just like if you're watching a football game, the heavier guys on the football team, they don't get moved as much if they get tackled than a lighter guy. And so the lighter ones, they'll bend quite a bit as they go through this beam and hit the sensor down on the end. And the heavier ones, they won't deflect as much, and they'll hit somewhere over here. And so you get a way of separating the different particles based on how much they deflect as they go through that, that magnetic field. So then you can tell two things once you get to the other side. You can tell the mass, or the relative mass. You can compare the mass of the particles based on how much they deflect. And you can tell the abundance. By the amount of charge that hits this sensor, you can tell the proportion, like how many were the heavier and how many were the lighter. Once you have the information from a mass spectrometer, you can use it to work out an average for any sample of isotopes. So the two isotopes that we had were lithium-6 and lithium-7. When we passed it through our mass spectrometer, we determined the relative mass in atomic mass units, and we also determined the abundance. So there are only a few, 7.5% were the lighter isotope, and 92.5 were the heavier isotope. So you get two different quantities that you are given from mass spectrometer, and now we can use that to calculate the average atomic mass. So the average atomic mass is the number that you find on your periodic table, because all the elements on the periodic table include the isotopes, all the varying isotopes for each element. So to determine the average atomic mass, you got to use the information from that mass spectrometer, and it's a pretty simple formula. You just multiply the mass of each isotope by its abundance, and then you add it to the mass of the other isotopes and their abundance. In this case, we only have two isotopes that we have information for, and so we can work out the average atomic mass, and we'll take the first one here, 6.02 atomic mass units, and we'll multiply by their proportion, which is 7.5% out of 100, and then we'll add that to the second one here, 7.02, and we'll multiply that by 92.5 out of 100%, and then we'll add those up. All right, I'm going to do it on my calculator here. So bracket 6.02 times 0.075 bracket plus bracket 7.02 times 0.925 bracket equals. So I get 6.945. 6.945 atomic mass units. So there you go. All those values off your periodic table are all average atomic masses of all the isotopes known for a given element. The last thing we're going to look at here are isotopes that are unstable. So unstable isotopes can decay or break down and give off chunks or bits of themselves to the surroundings. And that's called radiation, and those isotopes are called radioisotopes. So we'll use lithium-7 here as an example. And we'll use an example of three different types of radiation. So we got alpha radiation, beta radiation, and gamma radiation. The first type, alpha, gives off a pretty big chunk of the nucleus, 2 protons and 2 neutrons. And we represent that as a little He for helium, because helium also has 2 protons, and a little 4 to represent the total mass, right? And so what's left after that piece leaves here, if we cut out 2 protons and 2 neutrons, all that's left is 1 proton and 2 neutrons, which is hydrogen with a mass of 3. And so one thing you can remember with, this is a nuclear decay reaction, one thing you can always do when you're done to see if you did it right is add up the tops and the bottoms and make sure that they all equal. So 1 plus 2 equals 3, and 3 plus 4 gives you the 7 here, right? So that's alpha decay, and that's because that piece broke off and flies away. Okay, beta decay is really weird. Beta decay is when an electron is given off from the nucleus. Not the shells, the nucleus. This is so weird. So beta decay, you've got one of the neutrons, this is a neutron here, breaks down and becomes a proton. So you get an extra proton, more than what you started from. So instead of 3 protons, now there's 4 protons. So this isn't lithium anymore, it's beryllium. So nuclear change can sometimes result in a new element being formed. It has the same mass though, because it was one of the neutrons that turned into a proton. So the same mass overall, still 7 particles in there. And then to represent the electron that comes off, you use a -1 for the atomic number so that that still adds up, right? So 3 from the lithium here equals 4 minus 1. And then 7 plus 0 is the 7 that was there. So same thing, you can always just add the top and the bottom numbers to make sure that you did it right. The last one here that we're going to look at is gamma radiation. Now gamma radiation is electromagnetic, so no mass, and so no change to the element. It's still lithium, 7,3 here, but it's probably a little more stable now because it has given off a little bit of energy and the particles have shifted to be a little closer together to release that bit of energy. Gamma radiation is the one you often hear about in comic books, and sometimes it's used for like radiation therapy for people that have cancer, and there's all sorts of practical uses for that type of thing. There is also a little radiation source, alpha radiation source inside your smoke detectors, which is kind of cool. You have alpha particles being given off all the time by this little source inside of every smoke detector. And because of the charge of those particles, they're all positive, right? Because 2 protons. They act as a connection between a circuit. And if some smoke gets in here, well, maybe use different color. If some smoke gets in here, then that charge can't be passed from particle to particle anymore, and that trips a switch and makes the alarm go off. Right? So little alpha radiation in your house all the time. Alpha radiation is really big. It wouldn't penetrate your skin, so there's no danger of that being harmful to living things. Same thing with beta decay. It's pretty low energy and wouldn't harm you. With gamma, you'd have to have some pretty focused gamma to cause a problem. There's some background radiation all the time that we're bombarded with, and our bodies have ways of dealing with it. Usually means we're fairly safe. Okay, so let's try a few nuclear decay reactions here. We'll start with uranium 238, and you can see uranium on the periodic table here is number 92. And we're going to have uranium undergo alpha decay. And so alpha decay is a helium nuclei, and helium is element number 2, and it has 4 total particles in its nuclei. So that means that the atomic number is going to go down by 2, so that takes us down to 90, which as we can see is thorium. I'm thorium there, and the atomic number is going to go, the mass number is going to go down by 4, so it's 234. So there you go, decay of uranium-238. Beta decay, so if we start with carbon-14, which is the radioactive version of carbon that is used for dating artifacts, and we do beta decay on that. Beta, if you recall, is an electron, which we write a -1 there, and no change to the overall mass. One of the neutrons is going to turn into a proton, and so that means that the value, the number of protons increases, which means instead of carbon, it's now nitrogen. We'll have a mass number, atomic number of 7, and the mass number will stay the same. So as long as everything over here adds up to equal everything on the other side, then you know you did it right. And alpha and beta decay are the only ones that we're going to bother with. Gamma radiation doesn't change the mass of anything, and so you can include it with any of these and it won't change the outcome. In fact, oftentimes it does accompany other nuclear changes because there are energy differences between the start and end conditions. Okay, we'll talk to you soon.